Electrical field lines. Well, we have here a positive charge, and we have here a negative charge, and a few points in space between those charges. In the first point here, we can draw the electrical field created by the positive charge, which is in this direction, because in the previous movie of electrical field, we saw that the electrical field of a positive charge is away from the positive charge. We can draw the field from the negative charge, which is in this direction, because it's towards the negative charge. We've drawn this smaller than this one because we're closer to the positive charge. And the distance is r squared. We divide by r squared to calculate our electrical field. We have two vectors in the same point, vectors of electric field. We have to add them, and then we get this as our resulting vector. We do the same here in the next point. We have the electrical field here, which is away from our positive charge, and the field from the negative, which is towards the negative charge. This time E1 is a bit smaller, E2 a bit larger, because we are now further away from the positive but closer to the negative. We add them together like this. We can do the same here, which gives us a small E1 and a large E2, which when adding gives us this resulting vector. We could do this for all the points between those other points. We can do all points in space here, and then we would get a line of those points, and the line would give us, if we have a point on the line and we draw here the line which is touching our field line, then we have a collection of points, in fact, which gives us all the different field vectors, which is a line to represent our vector field. Maybe clear like this when we have our plus here and minus here, and this represents, for example, our vector field. So all those lines is a collection of points where when we draw a tangential force, a tangential vector, we have in fact in each point the vector field created by those two charges. So here we have a vector like this, here we have a vector downwards, and here a vector upwards. Each time we have to draw the tangential vector. This would be for positive and negative charge, a dipole field, and here we have two positive charges, too fast, and which is the same. For example, if you take this point and you draw a vector tangent on this line, you would have the vector in that point of the field. For example, we have here a charge negative which is 3 times as large as the positive charge, and then we get this schematic. Now this is the same as our dipole field, but a bit distorted. To remember, because this charge is larger, it has more influence on the field, so it pushes these field lines away. Some people have difficulty remembering how this looks like. Well, if you tilt your head a bit towards the right, maybe you can see a little heart in there, or a big heart in this case. One of my female students once saw this like that, and of course it's a little trick to remember it by, because when you tilt your head like this, it's a heart, and a heart normally would have this point on the bottom. Well, it's also the largest charge, which, if we would compare it with gravity, would be the one on the bottom. So if you doubt it, draw a heart with the largest charge on the bottom of the heart, or the point of the heart. We have some other electrical fields. We have a radial field, not others, but we have here a summary of the fields you have to know. This is a radial field, one point in the center, and all lines going away. We have a homogeneous field, which is in fact all lines are parallel. It's, for example, between two charge plates. We will be using that one in the future movies a lot. Then we have a dipole field, which you already saw with two charges, but you can also have a dipole field with, for example, an object which has one side positive and one side negatively charged. Okay, that was it for this movie.